For the hybrid orbital and molecular orbital models activity, we start by working with the hybrid orbital model, and then we get into the molecular orbital model. The hybrid orbital model is one where we imagine a bond to be formed when orbitals overlap and electrons are in that region of overlap. The orbitals that overlap are a blend of the atomic orbitals of the atom. They have been blended to give these new orbitals called hybrid orbitals, and those orbitals overlap with the orbital of the atom it's bonded to. That of the two atoms that are bonded together, the orbitals of those atoms overlap. Where the electrons are is where the bond is, and that's in the region of overlap of these orbitals. So for hydrogen, when it makes a bond with an atom like carbon, nitrogen, on the carbon, on the nitrogen, those orbitals, those atomic orbitals have been blended to give these hybrid orbitals that overlap with the 1s atomic orbital of hydrogen. So hydrogen does not get hybridized. We picture its atomic orbital being the 1s atomic orbital being spherical, having all the right properties to just stay as an atomic orbital. But for the other atom, the carbon, the nitrogen, etc., the halogen, its atomic orbitals have hybridized to give these hybrid orbitals that then overlap with the 1s atomic orbital of hydrogen if we're talking about a, for example, carbon-hydrogen bond. Now, to figure out how these orbitals hybridize, what we have to do is draw the Lewis structure of the overall molecule or ion that we're working with. And yes, for hydrogen, just leave it as the 1s atomic orbital. But for the other atoms, we figure out how many electron groups there are about that atom. If there are 4 electron groups, we need 4 hybridized orbitals, and they are composed of an s atomic orbital and 3p atomic orbitals. When they hybridize, we call those 4 hybrid orbitals sp3 hybrid orbitals. So when we have the number of electron groups being 4, we have 4 sp3 hybrid orbitals about that atom. When we have 3 electron groups about an atom, we get 3 hybrid orbitals. They are composed of an s atomic orbital and 2p atomic orbitals. So we call those 3 hybrid orbitals sp2 hybrid orbitals. There's one leftover p atomic orbital that ends up making a pi bond. When we have 2 electron groups, we need 1s, 1p for the hybrid orbitals. We make 2 sp hybrid orbitals. We have left over 2 p atomic orbitals that are used to make 2 pi bonds. When the hybrid orbitals overlap with like a hydrogen 1s atomic orbital or with another hybrid orbital, and we have electrons in that region of overlap, we call that a sigma bond. That's formed from a picture at like a head-on overlap of orbitals. Here is the hybrid orbital diagram of ethane, C2H6, and this is figure 1 we're looking at. So the Lewis structure we see to the right, and we see that each carbon has 4 groups of electrons around it, so that means that carbon needs the 4 sp3 hybrid orbitals. We draw them when we're drawing that total hybrid orbital bonding picture in such a manner that we try to show the tetrahedral shape of those hybrid orbitals. So on each carbon we will draw the 4 hybrid orbitals and we name them each sp3, and then we overlap them in the middle. So between the 2 carbon atoms we overlap those 2 sp3 hybrid orbitals, put a pair of electrons there, and then for the 6 hydrogens we draw the 1s atomic orbital. We put an H in the middle, indicating we're talking that's an H atomic orbital, where the hybrid orbital and the atomic orbital overlap. We put a pair of electrons, and we then have the molecule. Each one of those regions of overlap of the electrons is a sigma bond. So there are 6 sigma bonds that are between carbon and hydrogen, the sp3 overlapping with the 1s orbital, and there's a sigma bond between those 2 carbon atoms that is overlap of sp3 and sp3. This is the total hybrid orbital bonding picture of ethane. In figure 2, we have the total hybrid orbital bonding picture of ethene, C2H4. What we have is 2 less hydrogens in our molecule, so for each carbon there's 1 less hydrogen. The Lewis structure of ethene is shown to the right. So if we look at the groups of electrons about each carbon atom, we would see that there are 3 groups of electrons. That means we need 3 hybrid orbitals, and they are each one sp2 hybrid orbitals. So on each carbon, we draw those 3 sp2 hybrid orbitals. We name them. We make them overlap in the middle so that we get the sp2 sigma bond between the 2 carbon atoms. And on those sp2 hybrid orbitals, we draw an overlap with a 1s atomic orbital from hydrogen. We do that 4 times. Put electrons in, we have those 4 sigma bonds. Now, on each carbon, we have a p atomic orbital left over. So we draw those as are drawn here, the vertical lines that are the orbitals that are a little bit shaded. Remember that for the p atomic orbitals, there's 2 lobes. So we have the upper lobe and the lower lobe, and those then have a side-by-side overlap where electrons are found. Side-by-side overlap, we have a pi bond for that. So in ethene, we have then 1, 2, 3, 4, 5 sigma bonds and 1 pi bond. Okay, in our next molecule with it, which is ethine, C2H2, we have yet 1 less hydrogen on each carbon. So C2H2, the Lewis structure shown on the right in figure 3, and right in the main part of figure 3 is the total hybrid orbital bonding picture of ethine. Okay, so looking at our Lewis structure, we see that each carbon has 2 groups of electrons. That means we need 2 hybrid orbitals, and those are sp hybrid orbitals. So we draw on each carbon 2 sps. We make them opposite each other. It's a linear molecule. We make the sp hybrid orbitals overlap in the middle, making for that sigma bond between the 2 carbon atoms. And then we attach hydrogens to the left, to the right side, making for that overlap, putting the pair of electrons in for the carbon-hydrogen sigma bonds. And on each carbon, there are 2 p atomic orbitals left over. So we draw a vertical p atomic orbital, lobe above, lobe below, and then we draw a p atomic orbital on each carbon, which has a lobe going into the screen and a lobe coming out. Those are shown with dots. Well, the dotted ones are parallel. They overlap, making for 1 pi bond. The vertical ones are parallel. They overlap, making for the other pi bond. So in ethine, we have 3 sigma bonds, and we have 2 pi bonds. The hybrid orbital model turns out to be very useful for rows 1 and 2 of the periodic table, and people do extend it and use it for other elements on the periodic table. It's very commonly used by organic chemists. It works well for them, predicting angles, predicting when whether something can rotate about the bond. It has a lot of good qualities to it, but it is limited in that it cannot predict the magnetism of the molecule, and it turns out it doesn't work well for an odd number of electrons. For that, we need the more complete picture, the molecular orbital model. This one involves thinking of the wave nature of electrons. Definitely review your Chapter 9 lecture notes on the hybrid orbital model, on the molecular orbital model, to refresh yourself on all the details of those. Basically, what we have in the molecular orbital model is atomic orbitals of the atoms that are going to form a molecule. We imagine those atomic orbitals as the 2 atoms get closer together, interacting to make molecular orbitals. So it's not that the atoms on their own hybridize their atomic orbitals into these new hybrid orbitals. That's the other model. Rather, we picture as the atoms come together, their atomic orbitals interact with the atomic orbitals of the other atom, making for molecular orbitals. So the molecular orbital model has the orbitals about the whole molecule. It's a little bit of a different idea than the hybrid orbital model, where they're very localized. Okay, so we then, in our figure 4 here, we have the atomic orbitals for hydrogen shown on the far left and far right. Those, as the atoms come together, interact to make for these molecular orbitals that are shown in the middle. That is the molecular orbital energy level diagram there in the middle. It is composed of 1s atomic orbitals interacting in a head-on fashion, so that's a sigma kind of MO that we get. The lower energy one, because energy is on the y-axis, that's called the sigma 1s because it's made from 1s atomic orbitals. The higher energy one is called sigma 1s star, composed of also 1s atomic orbitals interacting in a non-favorable way. Star implying anti-bonding, it disfavors bonding. Putting electrons there does not help bonding happen. Putting electrons in the lower energy one, the sigma 1s MO, does help bonding occur. And to see the diagrams for justifying this, look in your Chapter 9 lecture handout. So this would be the energy level diagram where the MOs are shown in the middle for hydrogen, or any row 1. That would be any hydrogen type diatomic, any helium type diatomic. Diatomic meaning 2 atoms. Now, when we get into row 2, we have to consider the 2p atomic orbitals and how they interact. They interact in a head-on fashion, giving us sigma 2p and sigma 2p star MOs. They interact in a side-by-side way, giving us pi, remember side-by-side interacting, pi 2p atomic orbitals, 2 of those, and 2 pi 2p star MOs. So when 2p atomic orbitals come together, those are shown on the right and left side. They interact, giving us the MOs that are shown in the middle. For O2, F2, and Ne2, so those that are on the right side of the periodic table for row 2, the way the 2p atomic orbitals interact to give us the sigma and pi MOs, that's shown in the middle of our diagram. It looks like that. We have lowest energy, sigma 2p, next in energy, 2 pi 2p, next 2 pi 2p star, and then lastly 1 sigma 2p star MO. Now what isn't shown in this figure 5 on the diagram on the left side, what isn't shown is the way the sigma, the 2s atomic orbitals interact. We're only looking at valence electrons because core electrons, the 1s atomic orbital electrons, we picture them as not forming MOs as atoms come together because they're too bound just to they're too close to the nuclei to be interacting with some other atoms' atomic orbitals. So we only look at the valence electrons and their interaction. So for a complete molecular orbital diagram for O2, F2, and Ne2, what we would have to do is below sigma 2p, we would have 2 MOs. We would have at the very bottom a sigma 2s MO. A little above that, we would have a sigma 2s star MO. Then we would go to sigma 2p, pi 2p, pi 2p star, and finally sigma 2p star. Now for boron and for B2, C2, and N2, so they're a little bit to the left in row 2, it turns out that the sigma 2p and the pi 2p MOs flip-flop energy-wise. So the MO orbital energy level diagram for B2, C2, N2 would have at the very bottom, not shown, sigma 2s, higher in energy, sigma 2s star, next pi 2p, then sigma 2p, then pi 2p star, finally sigma 2p star. That is shown and filled in for B2 here in figure 6. So we see the atomic orbitals of each boron atom on the left and right sides. Each boron has 3 valence electrons, so those are shown. Then those atomic orbitals interact to give us the MO, that's the molecular orbitals that are shown in the middle of our diagram. So we have the MO energy level diagram, sigma 2s, then sigma 2s star, then pi 2p, then sigma 2p, then pi 2p star, then sigma 2p star, going up in energy that way. So we have 6 electrons. We put them in starting at the bottom, spin up, spin down, and then go to sigma 2s star, spin up, spin down. Then we get to the degenerate pi 2p MOs, and we put 1 electron in each. So that would be our filled in molecular orbital diagram of B2. And we can use that to determine properties such as electron configuration, bond order, and magnetism. So that's shown next. The molecular orbital electron configuration of B2 would be sigma 2s 2, sigma 2s star 2, pi 2p 2, because we have those MOs with electrons, 2 in each. And the bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2. So let's go up to our diagram again. The bonding electrons are the sigma 2s electrons and the pi 2p electrons. The antibonding electrons are the sigma 2s star electrons. Alrighty, so what we have for bonding electrons 4, antibonding 2, So we have the bond order equal to 4 minus 2, that whole quantity divided by 2. The bond order is 1. That is, the meaning of that is it's like a single bond. If we have a bond order of 2 in bond strength, that's like a double bond. That's a stronger bond than a bond order of 1. We can have up to a bond order of 3, and that's the strongest. We can also have half integer bond orders. We can have values of 1/2, of 1.5. The bigger is the bond order, the stronger is the bond. A bond order of 0 means no bond. We can also decide upon the magnetism. Is it paramagnetic? That is, does it have at least one unpaired electron? Or is it diamagnetic? Does it have no unpaired electrons? So we look here and we see we have 2 unpaired electrons. It is paramagnetic. Alrighty, so that's the intro. So you may skip, as usual, the pre-activity. And then we get to the report. So we're in problem 1, we're drawing Lewis structures, and on the structure you indicate the bond type, so just use notation, of course, sigma pi. And then you are writing what the shape is, bent, etc. You are giving the bond angles, 109.5 or whatever it happens to be. And then you are identifying all of the atomic and hybrid orbitals on each atom. So for carbon, what are the orbitals? Be sure to include, if there are any atomic orbitals, don't forget those. So you're including all hybrid and atomic orbitals. You're doing that for, of course, CH3F, COCl2, NCS minus, where the Lewis structure is already drawn for you. And then you're doing those, drawing 2 total hybrid orbital bonding pictures. So review what was in the introduction, look back at your Chapter 9 handout notes. One thing that we did not consider in the introduction of this is what to do when we have a lone pair of electrons, because we have that in the molecule NH3. We have a lone pair on the nitrogen. Well, that lone pair is a group of electrons that is in a hybrid orbital. It's just that that orbital doesn't overlap with any other orbital because it's a lone pair of electrons as opposed to a bonded pair. So in your structure, do the best you can to show the shape of the molecule. And of course, you're drawing the hybrid orbitals on it. In that way, you're showing the shape. You're naming each orbital, name all the hybrid orbitals, any atomic orbitals. You are overlapping to make bonds and putting electrons in that bonded region with using arrows. You're showing any non-bonding electrons, hint, hint. You should show them on the nitrogen. You're labeling the bond types, sigma, pi, and you're stating bond angles. And you're doing that same thing for HCN. So carefully, first off, draw the Lewis structure so you know what you're working with, and then get into the hybrid orbital, total hybrid orbital bonding picture. It's a little trickier with HCN, just do your best. And don't forget to give all the information asked for. In problem 3, now we're working with the molecular orbital model. So you're given the molecule or the ion to work with, and then draw the energy level diagram. And so you need the MOs, and you're asked here to also include the atom energy levels on the outside. So you'll have the atomic ones on the left and right. Down the middle, you'll have the molecular orbital ones. So for N2, you're doing that. You're writing out what the orbital electron configuration is, calculating the bond order, stating whether it's paramagnetic or diamagnetic. Then you have now N2 plus to work with. You're removing an electron. It will look very similar, but slightly different stuff in it, of course. And based on the bond order of N2 and N2 plus, which has a stronger bond? You're working with then Ne2, so be sure that, of course, you're choosing the right molecular orbital energy level diagram. Based on the bond order, is Ne2 molecule likely to exist? Then you're working with Cn minus, running through all of this stuff with it. And that's it. So when you are happy with your work, scan it as a PDF file and submit.